Hello everyone, in this video we're going to be talking about E1 reactions and their mechanisms. The E1 reactions compared to E2 reactions are relatively easier to understand and they're not that complicated. So let's start out with a generic reaction. Just like an SN1 mechanism, an E1 mechanism will take place in two steps where, suppose if I have an alkyl halide, and I'm going to go ahead and take in a secondary alkyl halide here. The first step is going to involve a loss of leaving group. So I can have any leaving group here. So I'm going to take a chlorine here. So the first step is going to involve loss of leaving group. And once the leaving group is gone, you make a carbocation. And in this particular case, obviously, we're making a secondary carbocation, and you have this chloride leave. Now, these E1 mechanisms, they are going to be taking place with a weak base. So I can have either a water or methanol as my weak base here, and those are going to be your typical weak bases that's going to be using in E1 mechanisms. After running the first step, your second step is going to be different than what you have seen in case of SN1 mechanisms. So in SN1 mechanism, the second step involves the attack of nucleophile, but in this particular case, the second step is actually going to be a weak base, which is also a weak nucleophile technically, is going to be coming in and it's going to be grabbing the beta proton. So it's going to grab this beta proton here, and in the process is going to make a double bond. So you, at the end of the day, you're still going to have an alkene made here. And obviously you're going to retrieve H3O plus here. So that's going to be your two steps in E1 mechanism. So the first step is going to be the formation of carbocation, which is also going to be the rate determining step. And your second step is going to be the weak base grabbing the proton. So how would you know that a particular weak base or weak nucleophile is going to be acting as your nucleophile or a base? Because water or ethanol, they are going to be the weak bases and the weak nucleophiles, so they are capable of doing an SN1 and E1 mechanisms. So you always going to have a competition between an SN1 and E1 mechanism, and elimination reactions are going to be favored when you have a heat involved. So in this particular case, you're going to have this reaction being heated. If you do this reaction at room temp, you're going to have an SN1 mechanism instead. So let's look at your kinetics and why it's going to be called an E1. So obviously, E stands for the elimination reaction, and 1 means it's going to be unimolecular. So if I go back to my rate determining step, you can clearly see we have only your alkyl halide being involved in the rate determining steps, so it's going to be a unimolecular. So when I go ahead and write down the rate of this reaction, it's going to be some rate constant K and your alkyl halide. And obviously, remember, you don't necessarily have to have only halogen as your leaving group. You can have some other leaving groups as well, and obviously the most common ones are going to be your tosylates, like OTS and OMS. So the same story is going to be applied there as well if you have another living group in there. So like I said earlier, your SN1 and E1, they always kind of tag along with one another, and they're always going to have a competition. And you can, if you do this reaction at room temp, your SN1 product is going to be favored, and if you heat this reaction up, then your elimination product is going to be favored. Now, in terms of types of substrate and bases, it's going to be very simple. It's going to be similar to what you have seen in SN1 mechanism. You're going to have a tertiary alkyl halides doing your SN1 and E1, followed by your secondary alkyl halides, and you don't really have your primaries doing your SN1 and E1. So remember, this is going to be the order for both E1 and SN1 mechanisms. The question is when it's going to be when a particular reaction is going to be an SN1 or an E1, and that's going to be typically the case. If you do run a reaction at room temp, then you're going to have your SN1 being the major product, and you may have a little bit of E1 product as well. Because when you do the same reaction at an elevated temperature, your E1 in that case is going to be the major product, and your SN1 would be the minor. As far as your stereochemistry go, your E1 products, they're almost always going to follow the Zaitsev rule, which means your most substituted alkene is going to be made in this particular case. Remember, in case of E2, you have the option of making a Zaitsev or a Hoffman, depending on what type of base you're using. But here, for the most part, you're going to be making your Zaitsev product. And as far as your bases go, remember your weak bases and weak nucleophiles, they are going to be going together. So some of the weak nukes and weak bases that you really want to be aware of, one of them is water, you got methanol, and you got ethanol, and stuff like those. So those are the most common that you're going to be actually seeing in sophomore organic chemistry. Just a little bit more on the mechanism. It's not going to be any different than what I have written over there, but I can just go ahead and copy a part of that. So remember, your first step in either case is going to be the same whether you're doing an SN1 or E1. So I can have this as in a chiral center. It really doesn't matter. So your first step is going to be the loss of leaving group. You make this carbocation. And if you're making a carbocation, always kind of be on the lookout for carbocation rearrangement. Like in this particular case, there is no rearrangement possible. But even when you doing your E1 mechanism, you can still have a carbocation rearrangement because you're making a carbocation. And then if you were doing an SN1 mechanism, then your nucleophile would attack onto the carbocation here. But in this particular case, your nucleophile, which is also a weak base, is going to be grabbing the proton. And remember, when we're looking at which particular proton it's going to grab in, because we got two protons there. I got this right there, the yellow one, as one of the protons. That's going to be the beta, and you got this other one, the green one, that's another beta. So you have a possibility of making two products if you remove the other yellow proton. And if you remove the yellow proton, you're going to be making a other product, which is going to be your Hoffman product. But remember, this is going to be the minor in that case. Your E1 mechanism always going to give you the Zaitsev product, which is going to be the most substituted, and obviously it's going to be your, in terms of stereochemistry, it's going to be the trans product as well. Because in this particular case, there's not much restriction as far as having your leaving group and your alcohol as an anti-elimination. So this, as a result, this is always going to be the trans and the Zaitsev products. So that's all you really have to know about the E1 mechanism. E1 not very commonly performed because you're always going to have a fear of running an SN1 along with it. And anytime you actually have to make an alkene, you are going to be better off running somehow an E2 mechanism rather than an E1 mechanism. But just because it's not very beneficial, that doesn't necessarily mean you're not going to be seeing that as we move along. You will be seeing those in some other cases, especially in alcohols and all that, when you're trying to dehydrate those alcohols using acids. All right, so if you have any questions on any of those, feel free to leave any comments in the section below.